Okay, now we're going to apply this idea to something that is very important and at the same time very confusing. So let me start with something simple. The Earth rotates, right? So hopefully you know this, and I think this picture is beautiful, that sometimes myself and others make the mistake of talking about the sun going around the Earth. That's what it looks like to us, but of course that isn't what's happening. What's actually happening is that the sun stays pretty much fixed in space and the Earth is rotating around its axis. So this beautiful picture here shows India and China and Japan, and for this picture, the North America, the United States, is actually in daylight right now. So the Earth is rotating around its axis. But we just talked about the fact that if you're in a rotating system, you're actually in a non-inertial reference frame. And this is something that I've mentioned before, and we're going to talk now about what actually happens. And this is going to be a little confusing, and part of this is that normally we ignore this. So this is a small effect. We normally consider it negligible, but sometimes you might be asked to solve for it and understand the details. So let's think about how the Earth is rotating. You know the period of the Earth's rotation. It takes 1 day for the Earth to rotate all the way around. Not too bad. So we can define the angular speed as 2 pi divided by the period. So that's 2 pi divided by 86,400 seconds. So then, that didn't work. We can find what the linear speed at the surface is. So this is effectively saying that because the Earth is rotating at this angular speed, how fast am I going as a person standing on the surface of the Earth? So every object on the surface is going this fast, simply from the rotation alone. And we can find this, and this is always true. So this is just a general idea that if you have a rotation speed, this is supposed to be a circle, bear with me, that the linear velocity you get at a point is equal to your angular velocity times radius. That's general. So we can take this omega, this angular speed we found, multiply it by the radius of the Earth. Now the radius of the Earth is a very big number. And so we actually get a fairly fast velocity at the surface. Now you don't normally feel this 464 meters per second, right? That's half a kilometer per second. Now, part of why you don't feel this is because all of the air around you is also moving that fast. Everything around you is moving this fast, so you don't really notice it. But there is one little detail that actually will show us the difference, and that is going to be involving forces. This is where it gets a little tricky. So think about a scale in a non-accelerating situation. We would say that the scale is pushing up and gravity is pulling down, and that because our object here is not accelerating, right? Non-accelerating means A equals 0. We also get to say that our net force equals 0, right? So this is what we normally say. So the spring force here, again, you can think of this like normal force, but the book introduces this idea of using a scale as a way to measure weight, and that depending on what acceleration the object has, you measure a different weight. And really, we're measuring the normal force. So now, consider your rotating Earth. We again have our object, and we're now considering it on the equator. So that spring force is away from the Earth. Our gravitational force is towards the Earth. But now we must have a centripetal acceleration, right? We have an acceleration that's in basically the r direction. So this is going to be a little bit hard for me to draw, but for this point here, remember that my r hat is towards the center, and my tangential in this case, because you see your equator coming kind of out and into the page, your tangential is going to be into the page. And then you can call z up or whatever you want. So our acceleration is in the r hat direction. It's towards the center. That means we have a net force towards the center. But there are only two forces acting on our object. That is something that everyone should agree on. We have the gravitational force, and we have the normal force, or the spring scale force in this specific case. But now we need a net force. What that means is that our two forces are not equal in magnitude. Here we said that they were, here we say that they aren't. So this is where the argument gets a little bit tricky, and I'm not going to do out the math that the book does. So because we have an imbalance in forces such that we do have a net force towards the center, this means that your spring scale force is actually less than your gravitational force for this situation. But this is what we would actually measure as the weight. So over here, if we call that equal to weight, well, clearly we've done something a little bit wrong then. So what this means is that whenever we're working in our circular rotating Earth system, which almost all of our physics problems have been, that g, little g, where we say that this is equal to mass times gravity, this little g is actually kind of a lie. That little g actually has a small correction made to it to account for this rotation. So the book goes into the math. I don't want to worry about that too much. We can keep using the idea that g is 9.8 meters per second squared. But the idea is that when you account for the rotation of the Earth, that shows you that gravity is actually pulling a little harder than you realized here. So let me try to clarify this and go through the pictures one more time. I'm going to call this gravitational force in the rotating side that, where capital M refers to the mass of the Earth, little m refers to the mass of my object, and the book's referring to it that way because that is true gravity. This is the absolute real gravity occurring. This is mg. This is what we normally say. This is actually fudged just a little bit because here we see that this is equal in magnitude to our spring force, but here this true gravity is bigger. So what that means is that mg is actually a little bit smaller than our true gravity force. You don't actually need to worry about this in general. You can keep using this, it's fine. But where this matters is if we are thinking about what this scale is going to measure if it's on the equator versus when it's on the North Pole. So if instead we think about our scale on the North Pole, now what do we need to worry about? Well, now we have the spring scale force up, and we have our gravity force down. Now this is still, I'll write it as m on m, that way. But what's the net force there? Is this object at the very North Pole going in a circle? Nope, it's kind of rotating in place, but it's not actually going in a circular path. So what that means is for this one, net force equals 0. So this is where it's interesting. On the North Pole, your spring scale reads exactly the correct gravity, but on the equator, your spring scale and your gravitational force are not equal because you need a small net force towards the center for the circle to happen. So the point being that for the same object, if you measured its weight on a spring scale on the North Pole and the equator, you get a different value. So there's a correction to make if you want to be on the equator, and that's actually a correction that we just automatically make in our value for g. So I realize that this has been a little confusing, I hope if you want to see more of the math, the book does go through that more in detail. And those actually, I typically do a weekly problem that goes through this as well. So it's an interesting phenomena to think about, but it's not something that you typically need to worry about. A simplification we make usually is that we just use 9.8 here and not worry about that nonsense.